I'm Evan Haas. I'm a graduate student here in mechanical engineering and business. And I want to share with you today some work we're doing transforming carbon dioxide into valuable chemicals. So the motivation behind this project is something I'm sure most of you are familiar with, which is basically in every emission scenario that we look at, we need not just carbon reduction, but also carbon removal to achieve net zero. And the approaches that we have to doing that today, things like direct air capture or CCS, are these fundamentally added costs for their operators. There's no internalized benefit. And so they've been entirely reliant on public incentives to scale, which frankly they really haven't. And at the same time, we've built this entire carbon-based economy where the source of that carbon atom is fossil fuels. So for everything from plastics to fuels to paints to adhesives, if we want to phase out those fossil fuels, we need to find a new source of carbon. And so the sort of logical mental leap is, can we combine these two trends? Can we take carbon dioxide that we're emitting and use that as the source of carbon in our economy? And so that hasn't happened, and the question is why? Well, it's just too expensive. If we look at the simplest carbon-based fuel, carbon monoxide, it's known as synthesis gas. It's about a $60 billion market, and it costs around $600 a ton today for syngas. But you can use electricity to go directly from CO2 to syngas using electrolysis. But it costs around $800 to $1,200 today to actually do that conversion. And so again, it just hasn't been commercialized. But what we've done is, as part of this project is shown that we can go from that current metric to around $350 a ton using a combination of energy efficiency improvements while simultaneously pulling out the most expensive pieces of those systems. So today I want to tell you just about one of the technologies that we're using to do that, like Rena mentioned, DNA. And so maybe I'll start a little bit with the fundamental problem here with electrocatalysis. So in industry, there's sort of these two models of electrocatalysis. The first is what's called homogeneous catalysis, where you take your catalyst, you just disperse it in solution, and that allows you to use these soluble, organometallic, cheap catalysts that perform pretty well. And it also means that they're dispersed in solution. They can interact with your CO2 quite well, which is also dispersed in solution. But the challenge is they become physically removed from your energy source, your electrode. And so those electrons have to literally jump from electrode through solution to your catalyst to reduce your CO2. And that distance comes with an energy penalty. And so these systems, pretty inefficient, haven't been commercialized. Something like a hydrogen electrolyzer, which is sort of the big commercial application of these so far, they solve this by plating metallic catalysts directly on your electrode. And this solves that adjacency challenge, right? But it introduces a new one, which is these precious metal catalysts are incredibly expensive. They're things like platinum and iridium. And so again, in CO2 electrolysis, they just haven't achieved any kind of commercial viability. But what we wanted to do with this project is sort of combine the best of both of these using DNA. And so we're a bio-inspired project group. And so the inspiration here came from sort of organic chemistry, where these molecules, these catalysts, are tethered in biology. Can we mimic that in our systems? And so we take DNA not as a biological material anymore, but actually as an electronic one. DNA is conductive. And so we take one half of our double-stranded DNA helix and we just tether it to the electrode. We take the other half and we tether it to our catalyst. And when we flow those together in solution, they zip up. There's sort of that hook and loop analogy. And so that tethers the catalyst really nicely to our electrode. And it means that catalyst is free to float around in solution, interact with CO2, but it is still electrically grounded to that electrode. There is a really efficient transfer path for electrons to get from electrode through DNA to the catalyst. And so the impact of this is actually pretty dramatic. It means that we get about 30% better cathodic energy efficiency than any electrolyzer for CO2 electrolysis today. We've also shown that catalysts tethered with this tech last orders of magnitude longer, which means lower OpEx. And we do all of this while maintaining pretty high product purity. And so we actually just founded a company based on this, Helix Carbon. I'm joined by Professor Ariel First, who's back here as well, and David Brown, who was supposed to be giving this talk, but is currently in MGH about to become a father, so you guys get stuck with me instead. And what we're building here is this drop-in, self-contained carbon conversion system that circularizes the carbon cycle at industrial facilities. So our vision is we pull in the CO2 from an industrial emitter, we convert it to the fuel that they need on site, and sell that back to them to power their industrial processes. So our benefit, of course, is we just capture that margin between our cost to produce, that $350 a ton, and the current market price for these fuels, while our customers get carbon neutrality and they get insulation from what's been a pretty volatile natural gas market. So like I mentioned, we're starting with syngas with a particular focus on the methanol synthesis industry in the Southeast US as a beachhead. But long-term, we also are expanding to other carbon-based chemicals with a particular focus on ethylene using some copper-based catalysts that we've also developed. And so I want to invite you, if this excites you or interests you, please come by, talk with us, and learn a little bit more. We'd also love any introductions to petrochemical companies who could take advantage of this kind of technology, as well as just introductions to passionate electrochemists who might be interested in joining sort of a technology-forward team like ours. Thank you.